Welcome back. This is the third part of control rectifier. In the previous two lectures, we discussed on the half wave. Now we will be discussing on single phase full wave control rectifier using the center-tapped transformer. So let us see the outline. First, we will be discussing on the full wave rectifier, its introduction, and how the center-tapped transformers are used for the full wave rectification purpose. Then we will do the analysis, computing the RMS output voltage. We will do the circuit analysis with different load types. So this load may be the resistive load, the combination of RL, and then we can have the RLE load. And then we will be concluding this discussion. So what is the introduction for single phase control rectifier? The basic key concept that we have been seeing that the control rectifiers will convert the AC signal to DC using the thyristors. So thyristors, we use silicon control rectifiers. The output voltage can be controlled by varying the firing angle alpha. So once we vary the firing angle alpha, we can control the output voltage. Thyristors turn off when current becomes zero. So this is the natural commutation process because we have the AC cycle. So at certain time instant, we will be getting the current to be zero. And the conduction angle that we have is beta minus alpha. Circuit turn off time depends on this conduction angle. And most of the application like DC motor drive, battery chargers, electroplating, welding equipment and so on and so forth, we are having the controlled rectifiers. Let us discuss the full wave single phase uncontrolled rectifier where we were using the diode. Now instead of using the diode, we will be using the silicon control rectifiers to make the rectifier to be controlled in nature. So this is the circuit diagram of single phase full wave control rectifier with center tap transformer. The input that we give is basically the AC sinusoidal wave, which is the single phase, and through this transformer we can step down the level of the voltage of the input. We are using two thyristors, T1 and T2, which are connected in the form of center tap transformer, and then single phase load is connected at the output of this rectifier. So SCR cathodes are commonly connected. So if you see the cathode of the SCR, it will be commonly connected. Single gate drive circuit can turn both the SCRs. So the gate 1 and gate 2 of these two thyristors can be turned on using single gate drive circuit. SCR must withstand twice the peak supply voltage. So the twice we have 2√2 times the V that the SCR has to withstand in the peak level. The center tap configuration provides better transformer utilization compared to the bridge configuration. So in the next lecture, we will focus on the bridge configuration. This lecture we will be discussing on the center tap, and here the main note is that the center tap is providing better transformer utilization factor. The operation with the resistive load in the positive half cycle was that in the positive half cycle operation, the thyristor T1 is forward biased and thyristor T2 is reverse biased. When we apply the gate pulse at omega t is equal to alpha, the thyristor T1 will conduct. Current will start flowing from the load resistance R and the thyristor T1. The T1 conducts at omega t equal to alpha, so alpha being the firing angle, and this will stop at omega t is equal to pi. In the negative half cycle, thyristor T2 will be forward biased and thyristor T1 is reverse biased, and when triggering pulse is applied at omega t is equal to pi plus alpha, the thyristor T2 conducts. Current will start flowing through the load resistance R and the thyristor T2. So thyristor T2 will conduct from omega t pi plus alpha to omega t is equal to 2 pi. The current will flows through the load in the same direction for both the half cycle. So if you see the waveform of the single phase full wave control rectifier with the resistive load, we can see the input, which is a sinusoidal wave with positive negative, and this is single phase. We are applying two gate signal IG1 and IG2 for the two thyristors. So this is IG1 is triggered at alpha, IG2 is triggered at pi plus alpha, and then we will be getting the output voltage and the output current. So the conduction will start from alpha and end at pi, and the next cycle will begin from pi plus alpha. So we will be getting the output voltage and output current, and this is what we have, the thyristor T1 and thyristor T2 voltage. The analysis of the resistive load, if we do, the average output voltage that we get is the VDC, which is equal to 2 root 2 V by pi cos alpha. Now, if we do this analysis, we find that alpha 0, we get the average voltage to be maximum. When alpha is 90 degree, the average voltage is 0, and alpha 180 degree, the average voltage is minimum value. So, the average voltage varies from minus 2 root 2 V by pi to plus 2 root 2 V by pi. Current can be estimated in the average by dividing the resistance from the DC value of the voltage. So 2 root 2 V by pi r cos alpha will give you the current average value. The RMS output voltage can be computed using this formula, and the RMS output current can be estimated by dividing the resistor value from the RMS voltage. So this is the RMS current of the resistive load. Similarly, we can do the DC output power, which is the product of VDC and IDC that we have evaluated in the previous slide. So here we can put the values and we can get the power. Average power is the product of VRMS and IRMS. So we can get the formula substituting the values of VRMS and IRMS. Transformer utilization factor is again one factor to be estimated, which is the ratio of the DC power by VA rating of the transformer. So we can get this formula. Now the operation of this control rectifier when the load is the combination of RL. So in the previous we have seen that the load was resistive. Now it is a combination of resistance and inductance. So characteristic wise this is similar to the resistive load, but since we have an inductive load, load current may be continuous or discontinuous depending on the inductance value. So we will be not getting a continuous supply of the current. It may be continuous or discontinuous, and inductance will oppose the change in the current, causing the current to lag behind the voltage. So in the resistive load where we saw that the current and voltage are in phase with each other, here due to the inductance the current will be lagging the voltage. So if we talk about the current mode, we can have a discontinuous current mode where the inductance will be low and the current will reach to be 0. In the continuous mode, generally when the inductance is high, the current never reaches to 0. So let us see the discontinuous current mode operation. When the inductance is low, load current will be discontinuous and thyristor will be conducting for less than 180 degree. Thyristor T1 will conduct from omega t is equal to alpha to omega t equal to beta. Thyristor T2 will conduct from omega t equal to pi plus alpha to omega t equal to pi plus beta. Average output voltage that we get is depending upon the factor alpha and beta both, where the beta is the extinction angle determined by the circuit parameters. Now in the discontinuous current, if we see the average load current, we can compute by the formula VDC by R, and the output voltage RMS we can compute by this formula. RMS output current, which is VRMS by R, can be used to compute the RMS current. Now here we have the RL load voltage and current waveform in the discontinuous load current mode. So if we see the current I0, here the current is discontinuous. We don't have a continuous supply of the current from beta to pi plus alpha. Rest we have the supply voltage and the two gate signal, and then we will be getting the output voltage and the thyristor T1 voltage. If we see the continuous current mode, when the inductance value is very large, the load current will be continuous and thyristor will conduct for 180 degree duration. So T1 conduction generally starts with alpha and end at pi plus alpha, and thyristor T2 will start from pi plus alpha and end with 2 pi plus alpha. The average output voltage, which is the DC voltage, is given by the formula 2 root 2 V by pi cos alpha. And if we do this analysis again with different alpha values 0, 90 and 180, we find that average voltage will be 2 root 2 by pi in the rectification mode, and in 180 degree we have a negative value of the voltage, which is again indicating it is an inverter mode operation. At alpha 90 degree, the average voltage will be 0. So DC output voltage range will lie from minus 2 root 2 V by pi to plus 2 root 2 V by pi. When we have a negative, then it is a inversion mode. When we have positive, it is rectification mode. So RMS output voltage is again equal to V value. The current we can estimate in the continuous mode, which is having the factor of transient and the steady state, using this formula where we have the Z being the load impedance depending upon the combination of R and L, omega being the frequency in radian per second, and phi here is basically the load phase angle, which can be estimated as tan inverse of omega L by R. The constant A can be determined from the boundary condition, which is found at the current of conduction equals the current at the beginning of the next conduction period. So this constant A is basically determined from the boundary condition. Now this is the continuous load current mode in the RL for RL load where the inductance is very high. So if we see the current is continuous and never reaches to 0. We getting continuous supply of the current I naught. Here the inductance is very high. Now we will be having the RL load, and then together with that there is a freewheeling diode which is connected here, DF. So the freewheeling diode is connected across the RL load combination, and this is also known as half control converter or the semi converter. The role of this freewheeling diode is to provide a path for the inductive current when the SCR are off. So when these Thyristors are off, then the current which is flowing through this inductor will be discharged through this freewheeling diode. So it will have a path to discharge through the resistance. So it provides the negative voltage across the load resistance. Some of the advantage that we have with freewheeling diode is that it will improve the power factor. It will reduce the ripple in the output current. It will prevent the reverse voltage across the load condition, and it will improve the converter efficiency. Let us do the operation with the freewheeling diode in the positive half cycle and negative half cycle. So first let us see the positive half cycle. When the thyristor T1 is conducting and triggered at omega t equal to alpha, the current will flow from T1 to the load, and omega t equal to pi, the supply voltage will become negative. Thyristor T1 will turn off and the freewheeling diode DF will start conducting. Inductive current continues to flow through the freewheeling diode. So this is the positive half cycle. In the negative half cycle, where the thyristor T2 is conducting from omega t pi plus alpha, the current will start flowing from the thyristor T2 and flows through the load, and omega t 2 pi, the thyristor will turn off. So the freewheeling diode conducts again in the negative half cycle. The average voltage formula for the load combination with the freewheeling diode is root 2 Vs by pi 1 plus cos alpha, and the current we can estimate it by dividing this average output voltage to the resistance. We'll get the formula for the average load current. Output voltage here is always positive. Better regulation we get compared to when there is no freewheeling diode, and this will reduce the current ripple in the waveform. The RMS output voltage can be estimated, the root mean square voltage conducting from alpha to pi plus alpha, the given input voltage, and after integrating and simplification we will get this formula which can be used to compute the RMS output voltage. Here the Vs is basically the RMS input voltage per secondary winding, and alpha being the firing angle. Now if we have the voltage equation where the input root 2 Vs sin omega t is equal to summation of the voltage of the inductor and the resistor at the initial condition I naught, which is the current which is flowing through the inductor, omega t being alpha to pi plus alpha, that is the total conduction period, and the other parameters, that is Vs is the RMS input voltage and I naught being the instantaneous output current, and the parameters are resistor and inductor. So this is the differential equation for the voltage. The current expression for this, again we have the steady state and the transient part, and all the other quantities like Z is the load impedance, phi is the phase angle of the load, and again we have the constant A which has to be determined from the boundary condition. Now one boundary condition we can take is that the continuous conduction we have I naught at alpha is equal to I naught at pi plus alpha, which is equal to I naught. The other load combination, which is resistor, inductor and the source of EMF. So here the characteristic is that the circuit will be operating similar to half wave control rectifier with RLE load, Only difference is that the load current flows in both the half cycle. So load current will now depends upon the firing angle, the load parameter of the inductance, and the ratio of the battery voltage to transformer secondary voltage, that is E by Vs. So we apply this RLE load combination in battery charging and the DC motor drive where we have the back EMF E. Now we will be computing the critical firing angle for this RLE load. The minimum firing angle we will get as root 2 Vs sine alpha minimum, which is equal to E. And if we solve it, we get what is alpha minimum that we required, which is sine inverse of E by root 2 Vs. So this minimum firing angle that need to trigger the converter can be obtained, which depend upon the battery voltage as well as it depend upon the RMS secondary voltage. And if alpha value is less than alpha minimum, then there will be no conduction occurring. So let us summarize what we have discussed. Single phase full wave control rectifier, we are using center-tapped transformer here with the SCRs. Output voltage is controlled by varying the firing angle in the 0 to 180 degree, and there are different load combination that can be used where the resistive load is simple operation and the current flows in the voltage. RL load, the current may be continuous or discontinuous. When we use RL load with freewheeling diode, it will improve the performance, always having the positive output voltage. The RLE load we are generally using for the battery charging applications. Freewheeling diode improve the power factor and reduce the ripple. Converter can operate in different modes based on the firing angle. So once we change the firing angle, converter can operate in different modes of operation. Now the performance comparison for these load types in terms of the output voltage, the current, and the power factor, we can see it. So if we talk about the output voltage, we can see that 2 root 2 V by pi cos alpha is what we have in the resistive load, and this is same as in the RL load combination. In the freewheeling diode, we have a factor 2 which is disappearing, and then we have 1 plus cos alpha. RLE load can be variable because we have the E, which is the battery EMF. Current will be discontinuous in resistive load. In RL load, we can have continuous or discontinuous depending upon the value of the inductance. It will be improved when we use the freewheeling diode. And in case of RLE load, it will depend on the value of the E. Power factor, if we talk about, resistor load will be poor. RL is also poor. Using the freewheeling diode, we can make it better power factor, and RLE load, it is variable in nature. So this complete our discussion on single phase full wave converter with center-tapped transformer. In the next lecture, we will see the bridge configuration in the full wave rectifier. Thank you for now.